Flat Earth debunked by HARTS. So what is HARTS? HARTS is High Altitude Retransmission Station, and I had to come up with this terminology just to avoid a certain word for now. It could look like this, or like this, or finally like this, which is known as satellites. And I don't mean the internet satellites or any other sort of satellites. Talking about the broadcast satellites, those that you point your own satellite dish on the roof of your home to get reception with high accuracy. You must aim your satellite dish. So how can this debunk the flat Earth? As you see from this triangle, if we know the distance, and I'll show how we get the distance or where is the satellite locations. We get the distance and we already have the elevation angles. You can acquire it from some sites, so you can get the altitude. Now the problem is the same problem that we globe earthers been calling for years now, the same as the sun. You can never get the same altitude if you try to measure it from different locations. So we'll get now to the calculation through that site. So this site is called dishpointer.com, and as you see here, there's a map, and it displays a location and a line that represents the vertical projection from your location to the location of the satellite, which is on the equator, and you'll see why it's on the equator. As you see here, it's still pointing at the equator. Whenever you change your location, you get a different angle, and the line ends at the equator. This here, the dish data is the elevation and the azimuth, and we'll need to have azimuth of 180 when we start doing our calculations. But first, let's check some other satellites. So this one here, the line will appear and it will still show the equator. Pick another one, another one. So each line has a corresponding angle that if you are on that location, you can get reception from the satellite. So these sites don't fool around. So now let's start our calculations. We get the distance for the first one, but the azimuth is 184 here, so we have to make it 180 to get the most accurate numbers. So the latitude for that location is 2.76. We put it in this spreadsheet that I made, and then we get the elevation angle, 6.7, and then we start doing the same for few more locations. And regarding measuring the distance to the equator, there is three ways. The first way is you get the circumference of the Earth and divide it by 360, or you can look in a Gleason map and measure the distance from your location to the equator. Or the third way is it's very hard to find a flight south-north or north-south and measure its flight distance and compare it to the latitude lines, just to make sure that indeed every 1 degree represents 111.24 kilometers or close to that. So now our measurements for the same satellite are complete from various locations through different distances, and as you see there is a big the discrepancy between 5,300 down to 1,500. That's too much of discrepancy. The same, or sorry, for the globe output, there's some discrepancy in the first reading by around 3,000 out of 36,000. The origin of this error is most probably from the elevation angles, because they are only displayed in tenth of degrees. So if you add 5% or subtract 5% from the elevation angle, you will get a different reading. And I'll put a link to the spreadsheet, and you can do the same process with all elevation angles to see how the discrepancy of the flat earth model will continue, and this will not happen to the globe output. So here is how we get the satellite altitude and distance on the globe model. We have here the radius, and we have the uh, latitude line, which is an angle measured from the equator, and this here is a right angle. This line, this is a right angle here. So since this is a right angle, then this angle equals right angle minus the blue, and this is right angle, so this must be the blue. So just keep in mind. Now this green is the elevation angle, so we have two angles here, so we know the total angle. Now we have a right angle triangle that we know one of its sides. We don't know this one yet, know this one, know this one. We can get this from the I think the sine equation, because we know this this side of the triangle and we know this angle, so we can get the number 1, and then we can get number 3, and since we know the radius, then number 4 will be the radius minus number 3. Now that we have 1 and we know this angle, so we can get this side of the triangle, or this hypotenuse. So we have a hypotenuse and we have an angle, then we can get all this side of the triangle, which I call it 2a. Once I get 2a, I subtract 4 from 2a, and that would be the altitude. So 2a is the altitude minus 4. We get the altitude, and we have already 2 is the direct distance. I hope this video was useful. I'll put the link for the spreadsheet, but as you see, it's all simple trigonometry that we had in high school, and I hope you do it yourself. Don't just depend on my spreadsheet. Thank you all for watching.